Here we have the energy zone manifold. This is the smaller of the standard units, an energy 4. By 4 it means you have 2 zones at the bottom and potential for a boiler on the left, boiler on the right. It actually can do a lot more than 4 things. But anyway, let's move on. We'll just have a brief look at what exactly it does. Inside the 25mm thick high density insulation, you have a metal pressure tested manifold. And inside that manifold, you have 3 areas. The top area is where you would introduce any heat from any form of heat source, high temperature, low temperature, whatever. And then in the middle, you have a bypass chamber, which would return the water that hasn't been used by the zones back to a high temperature boiler. On the bottom, we have a return chamber, and this captures the water coming back from any zones having lost energy and allows that to be returned back from either left or right or any of the ports entering that lower chamber back to, say, a condensing boiler or a heat pump. So, very simply, top chamber is the high temperature flow input from any appliance. Mid chamber or bypass chamber would be, say, for instance, a conventional oil boiler, conventional gas boiler, or maybe a solid fuel appliance, where you want a high temperature going back to the appliance so you don't form condensation inside the chamber, the burning chamber, and damage the appliance. And then on the bottom chamber, this is what makes the energy zone unique. This is exactly where you catch the coolest water to return to boilers that need a low temperature, for example, heat pumps, condensing boilers, and the like. When you see there's a bypass chamber or exit on the right hand side of the internal waveguide at the top, what this does is that if water flows in from a boiler, say from the left port here, or from the right travelling through a pipe that passes through the unit, they both meet this baffle here, turn back, and then flow from left to right. So a boiler flowing from the right goes from left to right, and a boiler going from the left still flows internally from left to right. And this arrow represents a 100% open bypass, so there's very, very little resistance inside the unit. At the same time, if you have zones operating, you can then use the return bypass. So if, for example, your zones are coming back in and you want to feed the return water back to, say, a solid fuel boiler or a conventional gas boiler or whatever, then the bypass on the bottom will allow water to flow both directions. It's dynamic in that if there's an excess of water coming from the boiler, it'll flow downwards and back to, say, a condensing boiler heat pump. And if it's needed to go the opposite direction, then the bottom bypass does exactly that. Neutral point of a heating system is probably the most important thing to understand, because that's where you would join your safety equipment like safety valves or system cold feeds or filling points, your pressure vessels, and also at that area where the water would be travelling at its slowest, having come through from a narrower pipe into a bigger area. Any air in the area will start to slow down around the neutral point. So this area is also critical for with regard to pump location. If you're pumping to a boiler from a manifold, from the energy zone manifold, you pump on the return connection to the boiler. But remember, the flow to a boiler is the return pipe. Also, if you're pumping to a zone, for example, a zone would be used one of the pipes on the bottom, you'd pump on the flow out through the pump around the zone resistance and back in. So you always pump from the manifold outwards whenever that's possible. At the top of the manifold there are 3 additional ports. The left-hand one could be for a temperature sensor. In fact, it could be a boiler input. It could even be a zone output. So if you were to take a zone out, you take your flow, pump, and back around and into one of the returns, maybe an unused boiler return or side return, or into one of the returns at the end. This center connection at the top of the tree, center of the tree, but not necessarily center of the manifold, is the air trap or the venting port. that you would put an automatic air vent here, or an open expansion vent, or any way of introducing or exiting air from the system would be taken from here, because within that you have a trap created that catches any air bubbles and allows them to escape. So if the manifold is being filled with water from a boiler, the top chambers, you'll notice if you touch it on the outside when the system is operating, will be hotter than any water coming back from the zones, which of course will have lost its heat. And that's precisely what this is really, really good at. It allows the hottest water to be separated from the coolest water and allows each of those to be used for their respective duties. For example, the hottest water would feed zones, the return water, the coolest water would feed the boilers that needed the coolest return water. If you took away the metal so and just look, what you have is two distinctly different temperatures of water. You have a constant deaeration unit because this is such a bigger area compared to the pipe feeding it. The water velocity slows down, air travels to the top, and every time the water passes through the manifold, it deaerates. So again, you can see where an automatic air vent would be fitted at the top to release the air. And you can now also see on the left, you can have an input from a boiler, say at the top left hand side or the top right hand side, or in fact you could have two boilers, one at the left, one at the right. You could have a high temperature return, say for instance on the left, and a low temperature return to a different boiler on the right, or vice versa, a low temperature boiler on the left hand side with the return taken from the bottom chamber. You can actually, just as a matter of interest, take boilers in the vertical chambers, ports looking upwards as well. This one could be a flow up, where then any zone port leaving that would become a zone outwards, and your return back to the boiler could be any port leaving the lower chamber. So it's an incredibly versatile, simple little principle, but very, very easy to adapt to more systems. In this situation, we're showing a unit delivering heat on top. This particular unit is a heat pump heat exchanger from a split unit, but it could just as easily be a gas boiler, or even a wall-hung oil boiler, or an oil boiler upstairs, whatever. But you see that the flow comes off and the boiler and arrives into the top chamber. The return carries on down, and as with a heat pump or any water boiler that has a, say, small waterways, you'd put a strainer on the return back out of the manifold, catching any dirt that would go back in to block any heat exchanger that might be in the system. This is only necessary where the appliance itself requires a strainer. But this is where you would locate it then. If, for example, then you took a zone, maybe you want a radiator zone and you want a flow and return to each separate radiator, well then you take your flow from the top chamber, where you, if you are not using, say, a boiler on the left hand side, you could take flow from the top through the pump, head away through your radiators or on whatever on the floor, come back around, up through a non-return valve. You might have an isolation valve so that you could isolate that area, that zone, and back into the return chamber. If you say had a hot water cylinder, you would take your flow from the top port, or the left-hand port, which enters the top flow chamber, pulls down through the pump, up in through the cylinder coil, heats the domestic hot water, and back around. In this example, we show a non-return valve fitted here on the return port into the manifold, but that's because the pipe drops down, goes across, and rises back up, and in other words, it forms a heat trap. So, but if you were to go directly into the cylinder, then you would probably find it better to put your non-return valve feeding into the cylinder here at this location, which means when the cylinder is hot, heat won't drift back out and be lost on the pipework. If you had a circuit upstairs, you simply drop down below the unit, drop as far as possible. I like to drop maybe 300 mil, 400 mil, or 12 to 15 or 20 inches below the manifold, pump down, around and back up to your circuit upstairs. The non-return valve fitted on the return again will just catch any inadvertent heat drift that would otherwise drift up and heat the radiators upstairs when there was no heat being called for. So inside again now you see where the pumps are drawing from the hottest water for the zones. The pump on the left is going to, say, radiators. The middle pump here is connected on the flow pipe and is arriving at the top chamber and heating, maybe under for a heating or a cylinder or whatever. And then your right hand pump could be going upstairs. Any one of those pumps from any one of those ports on the chamber can go and do the job. You don't necessarily have to use a particular one for a particular job. What of course is critical is the flow must arrive in the top chamber. So at the left hand side or the top left hand side connection could also be a flow in, and your returns can literally go from any port that enters into the lowest chamber, either on the left or anyone underneath. So even though we've shown that this has a heat appliance connected, it still has some spare connections. Say for instance, this one could be used for a zone or an additional boiler, maybe a solid fuel boiler, and this could actually be another zone return coming back in. And then the same applies on the other side. You actually still have a port over here, and you have a spare port at the side, which we'll talk about as well separately in a while. But that means that this unit can actually handle a boiler and up to, say, 5 zones, again making it a very, very economical addition to a job. If we move on again, you see that we're now standing back and looking at the system. This really could not be simpler. It's by the book correct in how a system would be designed. Your neutral point, make sure the system de-aeration is done properly, the boiler is piped away, collecting the heat from the coldest part of the neutral point and delivering it back into the upper chamber. And each pump is pulling from the manifold and doing its respective job, heating the cylinder, but also pushing back to the boiler. So again, very, very neat, very simple, very cost effective. So the Energy Zone manifold is manufactured by Energy Awareness, powered by C-Box. Hopefully you'll find this informative. If you have any other questions, please contact us by email at info@nrgawareness.com, or you can contact us on telephone number 00353 21 4355728. Thanks for your time. Hope you enjoyed it.